Okay, I'd like to introduce our final speaker for this session. The speaker is Veronika Witzke, who joins us from the Max Planck Institute for Solar System Formation, Sonnensystemformung, is it?
Solar System Research.
Solar System Research, oh, excuse me, okay. And please go ahead.
Okay. Good afternoon. First of all, I would like to thank the organizer for giving me the opportunity to present my research here. And as we have learned from the previous talk by Diego, stellar magnetic activity is very important to understand if we are about to understand solar magnetic activity. In my talk, I would like to focus on a different aspect of magnetic activity, and this is how we can model brightness variations of stars on the magnetic activity timescale. So the physical processes that drives brightness changes on stars are very similar to the one on our sun. So the drivers on timescale smaller than a day are oscillations and convection. And the processes that drives brightness change on timescales larger than a day are magnetic fields that emerge at the surface. And if we want to go ahead and model brightness changes for stars, we can build on sophisticated solar models that can reproduce the TSI and SSI very accurately and extend them to stars. So let me briefly talk you through our approach, how we want to model stellar brightness changes. Roughly speaking, we need emergent spectra for different magnetic features and the quiet regions, which we get from a radiative transfer code. And this emergent spectra we then can use together with the surface distribution of magnetic features with time that we can, for example, for now, get very accurately for the sun. And then we get the time series, and we can derive the brightness evolution from the whole disk. In a 1D approach, we take one-dimensional structures for the quiet regions for spot umbra, spot penumbra, and faculae. And it is worth noting that the faculae were derived initially semi-empirically to match the solar emergent spectra. So then taking those 1D models, we run Atlas 9 code, it's a radiative transfer code, to get the emergent spectra. Then we take the emergent spectra, use the magnetic distribution, the magnetic feature distribution on the surface, and get the brightness change. So if we want to be more realistic, we have to go to three-dimensional simulations. For that, we can use 3D magnetoconvection simulations from URAM. These are Cartesian boxes, which we then can pierce with many, many rays in different viewing angles to get the emergent spectra by, again, using a radiative transfer code. And since we need many cubes to get a statistically independent average, for example, quiet stellar region, this approach is very computationally expensive. In order to cope with that, we developed a tool to speed up our radiative transfer calculation by 100 to 1,000 times. And this tool we will make publicly available because it is not only very useful for our calculation, but it can be even optimized in different filters, such as Meringue, B and Y filters, and the Kepler passband. So let me just remind you why we are interested in modeling stellar brightness changes. Over the last half a century, long-term trends of main sequence stars have been observed, and the ground-based observations captured the chromospheric activity by measuring the calcium-2 line and the photometric brightness variations in the Meringue B and Y filters. So from that, we got a regression by using 72 stars, where we see that with the chromospheric activity, our brightness change increases. So now we are interested how the sun fits into that plot. Then, by plotting in the sun from a view of so the sun as a star, we see that the sun, having its chromospheric activity level, lies well below the regression that was found. And we want to understand why. So in order to understand why, we first have to note that on this plot, we only see the chromospheric activity of the stars and their photometric brightness change. We don't know anything about their stellar fundamental parameters, such as the effective temperature or the metallicity, which might have an effect on the brightness change. And this is what I will show you in the next couple of slides, where where we investigate how stellar fundamental parameters will affect the brightness change. So let's start with the solar case. And on that plot, I'm showing the brightness change for the sun, and there are three components. The red component is the faculae contribution in the visible and near infrared. The blue component is the spot contribution to the brightness change, and the black component is the overall total brightness change, which is the sum of the faculae and spot components. Moreover, I show you here the Kepler passband and the Strengren B and Y filters, which are quite important for my investigations. There are two things that I would like to point out here. The first thing is that the total brightness change is very low, and this is because the faculae and spot contribution almost cancel each other out. The second point is that the faculae contribution is very noisy. And this indicates that Fraunhofer lines are a quite important contribution to the brightness change. And building on that, if we change the fundamental stellar parameter, we expect that the contribution from the faculae will change significantly. So our first study is the metallicity, and we looked at different metallicities in a range that ensures that those stars with this slightly change of metallicity are still sun-like or even solar twins. So as you can see, the brightness change in the Strengren B and Y filter and the Kepler passband increases with increasing metallicity. Moreover, we find that for a lower metallicity than the solar value, we have an anti-correlation. And this might explain why we see stars that have a similar magnetic activity as the sun, but show a spot-dominated behavior. And these theoretical results were also used to explain the brightness changes of the solar analog HD 173701. This solar analog has almost the same stellar fundamental parameters as our sun, and the only difference is the metallicity, which is twice as large. So moving on to another stellar fundamental parameter, we investigated how a small change of effective temperature will affect the brightness change. We use a plus minus 100 Kelvin on top of the solar effective temperature of 5,777 Kelvin. And as you can see, if we look at the slightly larger effective temperature for a star, we find that the brightness change drops and even becomes anti-correlated in the Strengren B filter. Whereas for a higher effective temperature, we find that the brightness change increases. So from these overall investigations, we find that the brightness change on the magnetic activity timescale for stars that are very close to the, that have fundamental stellar parameters that are very close to the solar case are at the local minimum. And to come back to the very first slide that I showed you, if we look at the hypothetical sun with a much larger metallicity, it will move up here. This doesn't mean that our sun has unusual parameters, but it explains its position on that plot. And so far, I've looked on the 1D calculations. So now we want to move on onto 3D calculations using Meringue cubes. So here, again, the 1D atmospheres that we used for this previous study. And now we want to use Meringue cubes, several series, one without magnetic fields and the other one with magnetic fields, to find the relation between the magnetic field on the surface of a star and the emergent spectra. So I will show you preliminary results for the Kepler passband, where we looked at the flux difference. And we find that if we look on the disk center, we find a darkening for small magnetic fields, which then increases with larger magnetic fields. If we look at the limb, we see an immediate increase in the radiation. And to come back to the metallicity effect, which I'm very excited about, is so we looked at two cases for now, and we see that the contrast for magnetic features increases with metallicity and decreases with smaller metallicity, which confirms our 1D calculations. So this is still ongoing research, and I'm very excited about getting everything done in all the calculations, which need some time because it's 3D MHD calculations. And other than that, we would also like to have more observed sun-like stars, such that we can compare our theoretical result to actual stars. Thank you very much for your attention.
Thank you, Veronika. This was very interesting. Are there a few questions? Let's see. I see one right here. Okay.
Metallicity from CU Boulder. Thank you for a very nice talk. I'm wondering, for the Meringue simulations, what is the boundary condition on the magnetic field, like at the lower part of the box? So I guess, how is the magnetic flux input into the simulations?
So we start with non-magnetic calculations. We evolve them until they reach a steady state. And then we plug in a magnetic field which has a constant magnetic flux. And then we let it evolve.
Thank you.
Maybe time for one more question. See one over here. Okay.
Hi, David Phillips, Center for Astrophysics. That was very interesting. Have you tried to, with your 1D calculations, have you tried to correct that activity versus R prime HK plot for known metallicities and temperatures? You showed an example where you can move the sun up. How many of those stars do we have all those parameters, and how much does it help if you apply them?
So we haven't tried to correct for the activity. So from the previous talk, we haven't done that. That's an idea that we also want to investigate. And the stars that we have in the sample, in this one, they are no really solar analogs. So it's difficult to see. So we don't have a really good example for the sun to test things.
We should move on because we have some excursions to get to. Please join me in thanking Veronika for that very nice talk. And let's thank all of the speakers from this session.